I will talk about close myself. First of all, happy birthday. Oh no, why does it go all by itself? What is this business? I don't understand. I don't want it to change every time. Can I borrow your glasses? No, your glasses. your glasses, yeah, I'm sure they're the same. No, they are not.
You just need reading?
I can't see, sorry. I can't see the thing. How can, yes, how can you arrange not to change the slides all the time? By itself. What do I want?
This is in French, it's absurd.
Yeah. You can help.
I can read it, but it's...
Yes.
Okay, présentation.
That's not full. I just want full screen. Yeah, full screen. Where's full screen?
Plein écran. Activez le... There you go. Last
Activez
one.
le mode.
Voilà.
See,
If
you
it was
read it.
diaporama,
Yes,
all you have to do
I
is read
have to
fast.
read it. Okay. So I will talk about that. Thanks. And of course, I want first to wish happy birthday. Now, I want to say that I'm personally indebted to David, first for his friendship, of course, all those years, but also because he has always been, and I'm sure I'm not the only one to say it here, he has always been ready to help whenever help is needed. And in some sense, everybody's good cause could become David's good cause. So he would really take everybody's good cause and help him with all the energy and the things he has. And I can give many examples, both in France, how much he has helped us, but also especially in Greece, where his help has been particularly useful to our colleagues in Greece. So thank you very much, David, for that. In fact, believe it or not, because of that, David has been proclaimed to be one of the 7 wise men in the world. And he has an official certificate and medal which has been handed to him by the President of the Greek Republic. And if you are very nice to him, he can even let you look at it for 5 minutes and get some wisdom. So he is one of the 7 wise men of the world. I can even show you some pictures of that. He is the wise man. I was only the host. Some local guy that we don't know. I can give you the name, but it won't help you very much. This is another picture like that. Beautiful place. Again. This is a very beautiful library, and we visited there, so it's a very pretty thing. And here is the place where, if you want to know where it was, here it is. So, gauge theories and non-commutative geometry. That's what I'm going to talk about. Motivation. There is a long story on that, which I will not go in detail. The first person who suggested to introduce non-commutative space with non-commutative geometry was Heisenberg, not surprisingly, because he thought that he would help. That was in the 30s, right? In the very early 30s, no, even early, 29. He wrote there were these ultraviolet problems, so he sent a letter to Peierls in which he was suggesting to introduce non-commutativity in space coordinates, just to put a cutoff and solve these problems. Peierls apparently talked to Pauli to Oppenheimer, and Oppenheimer gave this subject to his student, Mr. Schneider, just before the war, which was unfortunately for Mr. Schneider because Oppenheimer was busy during the war doing other things, so he did not help very much. Nevertheless, Schneider finished his thesis in 48, and the paper is published in 48. It was a very nice paper. I'm afraid many people did not read it. The reason is that in 48 the normalization theorem has come up, and people's attention was diverted to other things. Nothing happened to this approach. Then a different motivation was external fluxes, because Landau in 1930 solved the problem of the electron in external magnetic field, and there he found the non-commutativity, as you know, of the various components of the velocity operator. And Piles, who had received the letter, was the first recipient of Heisenberg's letter, applied this idea to. He just considered the motion of an electron, a free electron, but in a space with non-commutative geometry, and he found the lowest Landau level. So was this correspondence between. Then nothing very well. Several things happened in the middle, but the next important step I want to mention was the Seiberg-Witten map, in which we learned really the equivalence, how we can go from between the two pictures, and I will come back a little bit to that. Then another motivation is large N gauge theories and matrix models, which again will turn out to be like that. And finally, the most obscure one, which however I like it conceptually, is the construction of gauge theories using the techniques of non-commutative geometry. So, okay, I will go fast. Simplest case, we'll do some like that, some kind of constant. I call it Heisenberg case because theta is a C number now, right? Then you can make it Lie algebra. Then you can make quantum space structure or whatever. So there are zillions of possibilities. You define a derivative and the star product at the end. So people have worked in all these approaches, and they try to build field theories using one or the other of these things. I will only concentrate on a few things because I can't review everything. One of the things that I find disappointing in most of these works, including my own, of course, is that all computations can be viewed only as expansions in theta, in this non-commutative parameter. And somehow you lose whatever power you can hope to get from the non-commutative structure. Right? So this is maybe are there any more efficient ways? Can you quantize the theory directly in that space and forget about the other things? I don't know. And I will come back to it. This is equivalent to what the other question says here. Is there a BRS symmetry for a quantum field theory quantized directly on a space with non-commutative geometry, and how this BRS symmetry manifests itself? I will talk a little bit more. So, I will now talk about mostly large N field theories. If you have a phi I with index I to infinity, you can always, in a trivial way, re-express the thing as an integral over a continuous periodic variable, this trivial statement for your series. Now, if you do it with ON models, the phi-4th term will be non-local in sigma. Right? So the thing which is important for Young-Mills, which made it is possible to have this progress in Young-Mills, is that for Young-Mills theory, the resulting expression is local. So you get a local expression for that. In the other sense, given if you have a Young-Mills theory in a d-dimensional space, the fields are matrix valued, so the things you have there, then there exists always a reformulation of the theory, and this is just a trivial statement. There is nothing new there. There exists a reformulation of the theory in d plus 2 dimensions, in which the extra 2 dimensions satisfy this commutation relation Z1, Z2 to 2I over N. So this is a statement identity. It's a trivial statement. Well, there you can start arguing, but I have nothing interesting to say. You see, this formulation N does not have to be integer. So you can take any N. So this gives you a possibility to define Young-Mills theories for any N, not integer N's. Is there any physics on them? I have no way to tell you. The commutators become the Moyal brackets. The gauge transformation is the same thing. And this is the action you obtain. And as I say, these are defined for every n, and it's not necessarily an integer. So, if n can be a tensor. Now, how do you prove this statement? Well, the first step is just go to large n, and then it's a simple algebraic result. You prove that the SUN algebra becomes, when n goes to infinity, becomes the algebra of area preserving diffeomorphisms of a closed surface. I can prove it explicitly for a sphere or a torus, and I'm sure you can extend the proof. Because there I can do it explicitly because I have a pair of coordinates, symplectic coordinates that are globally defined. But even for any other surface, you can do it locally. Maximum. But this is an algebraic statement. Alternatively, you can do it the following way, which is more explicit construction. Take 3 variables, x1, x2, x3. Then you know that the YLMs can be written as is there a way to can be written as in these combinations with symmetric traceless tensors, right? A set of symmetric traceless tensors, and these are the fixed that. And then you choose inside SUN an SU2 subgroup. And Si, Sj are the generators of this SU2 subgroup. And you use this SU2 as a basis for SUN. And then you expand, you write every generator of SUN as symmetric polynomials in these 3 rows. And then this is the SUN structure constants in this unusual notation. The 3 SU2 generators, rescaled by a factor proportional to 1 over n, will have well-defined limits as n goes to infinity if you define them that way. And then they satisfy x1 squared plus x2 squared plus x3 squared equals 1. You see when n squared goes to infinity. And then, in other words, under this norm, the limit as n goes to infinity of the generators of T are 3 objects which commute and are constrained by this relation here. And then you just straightforward show that the commutator becomes the Poisson bracket of these 2 in this surface. So that so far for n goes to infinity. And now if you want to do it for arbitrary n, then you just parameterize the generators of SU2, which I had before, now I call them T, with 2 operators, Z1 and Z2, this way. And then the statement is, you prove that if you assume that Z1 and Z2 satisfy these commutation relations, then you prove that VT satisfy the SU2 algebra. And inversely, if you assume that VT satisfy the SU2 algebra, these satisfy the Heisenberg algebra. So this is the statement here. You can do the same thing with a torus. Then instead of picking up an SU2 subgroup of SUN, you find the U1 cross U1 quantum U1 cross U1, you have the operators Q and whatever P you call them, the Heisenberg operators, and again you expand. In fact, it's even simpler for the torus. Some reason so, why I was interested in this, what I call the techniques of non-commutative geometry. This started with a mathematical work by Alain Kohn. And his work was mathematical, he built all things. Then he, together with other people, he decided to look also at physics. And the interesting thing, that was in the early 80s, so it's many years ago. The attractive feature of this work for me was that you see, when we have a spontaneously broken gauge symmetry, we have the gauge fields and the Higgs fields, and we always say that in the broken phase, the longitudinal components are the Higgs fields. So there is, we try to identify them this way, but in the way we write them, the Higgs fields are totally independent of the gauge fields, and they have their own couplings and things like that. In his way of doing, it seemed that they were the same. So I say, oh, that's great, maybe we can do something. And then we tried, years passed, and we tried many things. And I will tell you where we stand now. Well, the idea is that the gauge transformations are diffeomorphisms with space-time and internal symmetries for whatever we call particle physics, right? So we have two kinds of gauge transformations. Question: is there a space in which all gauge transformations act as diffeomorphisms, and there is no difference? Well, Kaluza-Klein is an answer, right? So this is a possible answer. But if there are some things where you do it directly in our world, the answer is yes. Forget about Kaluza-Klein. You can always find a space mathematically in which all diffeomorphisms act, all gauge transformations act as diffeomorphisms. But usually the space has non-commutative geometry. It's a space of matrix valued functions. You have somehow to put the fact that they are matrix valued functions. So this is the motivation, the early thing I tried to do. So you say, so what? Well, I don't know. Maybe a possible way to unify gauge theories and gravity, I have nothing to add here. A possible connection between gauge fields and scalar fields. So this was the most promising thing. Yes, but it does not work, unfortunately. Now, why it does not work, I will come in a moment. In fact, the real problem is what I said at the beginning. When Kohn makes all this beautiful mathematical construction, things like that, although it's hard to talk, you need somebody to translate Kohn's to our language, but eventually when it's done, when you want to compute finally something, the only thing he knows how to do is to expand and make computations in ordinary flat space, right? So the thing was that these computations would have less parameters. I mean, this thing, once you start without, say, couplings for the Higgs, you don't have couplings of the Higgs. So the coupling of the Higgs is G squared or something like that. So is it possible in any way? Can we pose, I mean, you can translate it in measurable conditions, in a condition between the mass of the Higgs and the mass of the Z, or the mass of the W. So can we impose a condition on the theory? Maybe the theory has some hidden symmetry that says, and nobody has thought of it, that says that this mass was the other mass. Well, there is a simple way to study this problem, is to look at the normalization group flow of the various things to see if they have a fixed point. And it's a simple exercise, and the answer is no. There is no fixed point in this. And then you can even work in the time, I will not trivial equations, to find all possible relations. Is there any other relation among the 17 or whatever parameters of this capital? Well, the fermions really don't play any role. It's mostly Higgs. And the answer is no. There is no fixed point in all these things. So, a related question. Can we, that's why I come back to BRS always, can we quantize why is there is this problem? I believe that the problem is the way we compute. We do not compute in the space, in the initial mathematical space. We expand and make computations in flat space. How can we compute there? Well, to compute, you have to quantize in that space. The theory is classical as it's done, so you have to fix the gauge, and there is no consistent way to fix the gauge in that space. You can't complicate. Nobody knows how to do it. So, question, is there a BRS symmetry for this model? I don't know the answer. So, conclusions. Non-commutative geometry has come to stay. It's there. I mean, there's nothing, it's not you like it or you don't like it. Gauge theories are equivalent with gauge theories formulated in spaces with non-commutative geometry. So it is there. Now, it may be a trivial thing, but it is there. Whether it will turn out to be convenient for us to use is still questionable. It may be just a curiosity, nothing more. It will depend on our ability to simplify the mathematics sufficiently or to master them deeply in order to get new insights, which means that we need somebody with knowledge and imagination. Happy birthday, David. Yes, but it's on. Oh, no, because what they were doing is that they were just taking the model without the lambda phi to 4 term, putting a g square term. Then they have it there in 3 approximations, while it was obvious that the 3 approximations was wrong, so they were assuming arbitrarily that it was true in very high energies, continue somehow. The calculation itself was not meaningful because you start with
Perhaps I misunderstood that at some point you thought you had a map between matrix gauge theories.
yes,
So the matrix structure and functions of these two non-commutative variables.
yes, right.
Now, if you take the most general function of these two non-commutative variables, you'd be able to generate U infinity, some huge gauge.
Yes, right. Yes.
So you'd have to put
yes.
some restriction on the function.
Well, in fact, you see, it's not. Yes, you can generate whatever you want. Of course, because all this comes from n goes to infinity, the limit. So you start with n goes to infinity, and then what we prove here is that it's true for every n, and n is put there by hand in the commutation relation.
Even with a fixed n in the commutation relation,
Yes.
you need to restrict the kinds of functions of z1 and z2 to focus on.
Yes,
right?
you just take correct. You just take the Moyal, the simplest Moyal bracket you can get. That means you get the z1. I had the parameterization. You don't get any function for the sphere. The parameterization was different. Yeah. For the sphere, you get this parameterization here, right? So it's a very particular form. Z.
Everything is a function of these 3 guys.
Yes,
Of the function.
expressed this way, not everything, but it's expressed this way. Then they satisfy SU2 commutation relations, and then you make SUN by the way as before. Yeah. If you find more general parameterizations, you will find other. Not necessarily as U, I don't know how you will find. You may find whatever. That's why I said if n is not, for example, what is if n is not an integer? I have no idea what means.